talk about Born-Haber cycle. So what's the point of a Born-Haber cycle? Right, so when we're thinking about ionic compounds, this is all and only referring to ionic compounds, which of course are compounds made of typically non-metals and metals, and you have those ionic lattices, right? We want to understand about that lattice structure. We want to understand about the interactions between the positive and negative ions that make up that lattice. And you all know, I'm not going to hold it up, but you've all seen the lattice structure before. Just give me a nod, you know what I'm talking about, a lattice structure, that 3D arrangement, right? So when you've got a lattice, if we were to compare, say, a lithium fluoride lattice with, say, a magnesium oxide lattice, we'd expect the lattice to be a bit different. We'd expect the lattice to be much different in terms of the strength of interactions between the ions, and that would affect things like melting point, right? So the reason why, have a little think about it for a second if you can. What might be the major differences between the lattice structures of lithium fluoride and magnesium oxide? Think about the ions a little bit. Think about maybe Coulomb's law if you're a physicsy person. Have a little moment to think about that. I'll pause the video and I'll give you a minute to think. So the force of the attraction between oppositely charged ions is proportional to the magnitude of those charges. This is sort of simplified form of Coulomb's law, isn't it? It's also affected by another factor as well. So that's the charge of ion 1 and that's the charge of ion 2. The bigger those charges, the bigger that number, the force of attraction is greater. So what else will affect the force of attraction between two objects? Whether it's electrostatic or gravitational or whatever. So any thoughts? The force of attraction is also affected by the size of the ions, which affects the closeness to each other. So if the ions are small, they can get close to each other, and it's proportional to 1 over the distance squared. And this is a slight aside from what you must know. But you are expected to know that the strength of attraction between ions is dependent on the size of the charges and the size of the ions. The smaller the ions, the closer they can get, the stronger the attraction. It's just Coulomb's law. This is the kind of stuff, this is kind of fundamental stuff, which if you're prepping for, for university interviews, it's the kind of stuff you've got to go back to those fundamental ideas of electrostatic attraction and all that kind of stuff. So that's a bit of a long-winded background, isn't it? But it's important that you're aware of that basic idea, which we would have talked about in standard level bonding, and we'll think about a bit more in high level bonding too, I guess. Right. So if you want to study that attraction, what we can think about is this. If I use a generic M plus X minus ionic compound, we say that's a solid, and I want to study the strength of that lattice, we can theorize it on this idea of how much energy would it take to convert that ionic lattice into its gaseous ions. In other words, fully break all of the bonds in 1 mole of MX, right? It's a pretty hard thing to do in the lab. Essentially, you're melting and then turning it into gaseous ions, right? So that process there has got a name in chemistry. Someone's called that something. It's the lattice enthalpy of dissociation. I could never spell dissociation, but it's good enough. Right, that'll do. So lattice enthalpy of dissociation is that process there. Annoyingly, perhaps, when we study it, and have a little think for a second actually, is that endothermic or exothermic? If you think it's exothermic, point down. If you think it's endothermic, point up. If it requires energy, it's endothermic, point up. If it releases energy, point down. We think, yeah, loads of you pointing up. That's an endothermic process. Endothermic lattice enthalpy of dissociation. But in fact, what we more often than not consider is the exothermic opposite process, which is that. It's exactly the same thing, it's just the other direction. Again, that's even more difficult to measure. You can't get a mole of M plus ions and X minus ions in a pot and measure the energy released when they form. So if you're a geeky scientist and you want to find out about that lattice structure, because it is dependent on the size of the charges, it's dependent on the distance between them, but it's also dependent on the crystal type as well. And you've only learned about one crystal type, plus minus sodium chloride type structure, but there's also, is there one up there? Can't see one. But there's also all these other different lattice forms as well, where you've got one bigger ion than the other, and they pack in all sorts of fancy different ways, which is kind of interesting. But if you want to study that stuff, you've got to get your head around all this sort of thing. Right. So how do you work out that energy change? Well, the answer is you can't do it directly. You can do it indirectly. This is where Hess comes in. So Hess's law comes in. If we want to study an energy process, the energy change for a process is independent of the path taken, right? Yeah? Nod? That sounds familiar? So what we can do is we can look at something called a Born-Haber cycle. Now I'm going to build a Born-Haber cycle with you. I think we'll do it. I'll ask you what you think. So it's going to take up all of this space here. Do you want me to do it and you listen and then copy it up afterwards? Or do you want to do it as we're going along? I think, personally, I'd rather just talk it through like a lecture and you copy it up afterwards and I sit and wait for you to do that. And then I can, well, some people are faster than others, you can look at start learning the definitions, right? Okay, so we're going to do then. So you can just take it easy, sit back, listen, look, pretend to look interested, or something like that. So what I'm going to do is I'm going to end up on the right hand side with that big energy change, which this is a hugely important process, and I'll talk about the significance of it at the end as well. This is a big energy change. But what we're going to do is we're going to start here, okay? And this, you really have to be aware, is a graph of energy. And this is just like those energy profile diagrams, kind of, in the sense that the lines are representing some things and what the energy those things have. So if I start with a metal, M, it could be sodium, for example. In fact, I think I'm going to use an actual metal, an actual example. We can maybe even look at the numbers then. I'm going to use Na as my example, solid. And I'm going to say we're going to react it with chlorine, which we all know is a gas. Now, we have to write, whenever we draw one of these energy level lines, this is the energy of sodium solid and chlorine gas. And it's really important you draw the structures on these right, and you're expected to draw these in exams and so on, and they've got to have state symbols. Now we all know, because we practiced it the other day, that if you react those together you'll form sodium chloride solid. Sodium chloride solid, and that process has got a name we're all familiar with. I don't want to shout out what it might be. What's that energy process called, where you form 1 mole of the compound from its elements under standard states and the conditions? Anyone want to shout out what that is? You all know it, because you did tell me the other day. Cool? Formation. Yeah, it's enthalpy change of formation. So this energy process, the enthalpy change of formation, sodium chloride, we can look that up or we can measure it relatively straightforwardly. Okay? Right. And I've just told you that I'm interested in this process here, this lattice enthalpy of association. Do you want to make a note of that, actually, because I forgot to tell you that earlier on. The lattice enthalpy of association. That's the one that you're mostly going to be asked about and find out. And that's an exothermic process. And it's important, it's significant that it's big. So when you come to copy this at the end, it will be a big exothermic arrow like that. So that is delta H, we're just going to call it L, lattice enthalpy of association for sodium chloride. And you're going to learn that definition in due course. It's in your booklets that I gave you the other day, but we'll have to learn that in due course. So let me just tell you now, you can look it up and learn it later, but it's the enthalpy change when 1 mole of an ionic compound is formed from its gaseous ions. Right? And you'll see as we start to build this thing that some of those funky definitions like it has to be in the gaseous state and stuff, that's all because it all fits in well with this, okay? Right, so how do we get, so that is a sodium ion in the gaseous phase and a chloride ion in the gaseous phase. But I've made a mistake on here, haven't I? This isn't balanced. I forgot to do that, so be really careful. See how easy it was for me to make a mistake there. Half a mole of chlorine was required to make sodium chloride and 1 mole of chloride ions. So I've got to turn sodium metal into sodium gaseous ions, and I've got to turn chlorine gas into chloride ions. And that involves a number of steps, theoretical steps, all of which you can measure, allowing you to work out this one here. Okay, so I'm going to deal with one thing at a time. And I'm afraid you're going to have to sort of learn these, but it should become, once you've done it a few times, it should become relatively straightforward. Okay, so the first thing to remember is you need to turn the element into gaseous atoms. Okay, so the enthalpy change when 1 mole of gaseous atoms is formed from its element, I'm just doing one thing at a time here, is called the atomization energy. So delta H, atomization of sodium. So the enthalpy change when 1 mole of gaseous atoms is formed from its element. Well, it's not under standard conditions because this isn't under standard conditions, right? But this was. Okay, you'll learn the definitions, and that's obviously, to me, it's obviously, hopefully, it's obvious to you as well. That it's obviously that's endothermic. You have to essentially, you're turning a solid into a gas, right? So you have to put in energy. But we've also got to turn sodium into gaseous sodium ions. So what's that process called? Have a little think while I'm drawing it. So turning sodium gas into sodium. I've made this too small, but never mind. Sodium gas into gaseous sodium ions. You've all done this. You did it last year. We did it yesterday or the day before, whichever day it was. What's it called? That process. Again, take hands up here. Go on.
Is it ionization?
It is ionization energy. Right, so we've got to ionize. This is the first ionization energy of sodium. Well done. So delta H, first ionization energy of sodium. Right, so we've made sodium gaseous ion. So we're now part way there, aren't we? And we've ripped a mole of electrons off, and they must be drawn. Now, if you're doing this at A level, if you miss out the electron, I think which way around it is. I think it's A level they don't mind, and IB they do, but either way I mind. I want you to draw the electron so we don't get it wrong. And we've still got half a mole of chlorine gas. And again, we all know that that's endothermic. We all know that requires energy because we've studied it before. We've got ripping an electron off a sodium atom, or 1 mole of them. We've now got to we've got to do the same thing again. So we've got to atomize and then ionize the chloride ion. It's slightly different. So the atomization energy here is still called delta H, atomization energy. So it's the formation of 1 mole of chlorine atoms from its element. Okay, and that would give us sodium ions gas. They've not changed here in this process. Still got the electron. We've now got a mole of chlorine atoms. Now, I told you this, I think, the other day, so I'm just going to put it at the bottom, that the delta H of atomization energy, which is defined, as we'll learn, as the enthalpy change when 1 mole of gaseous atoms is formed from its elements, that process, right? Whoops. That process, that is equivalent to something that you've seen before that I reminded you of the other day, that most of you had actually forgotten. It's obviously a while since we've done it. Does anyone remember what that is? What have I got to do to turn chlorine molecules into chlorine atoms? What have I got to do physically to them? Yeah? Break a bond. So that is equivalent to, do you remember we said that the bond enthalpy is the enthalpy change, or the energy required to break 1 mole of that particular bond type? Right, you've got to break half a mole of those. Well, I remind you what that is. So the bond enthalpy equation, bond enthalpy for ClCl is Cl2 going to 2Cl. Because can you see that this value here, the atomization energy, is just half of the bond enthalpy of chlorine? So sometimes, the reason I'm telling you this is sometimes when you've got to look all these values up in your data books to get this value here, and you're like, I can't find the atomization energy of chlorine, and you're going, that's me stuck on this question, but actually it's just half the enthalpy, half the bond enthalpy of chlorine-chlorine bond being broken. That's a little cheat. I've only seen that question once or twice, but it's a good challenge. Right, and then the last thing we've got to do is convert the chlorine atoms into chloride ions. Do we know what that process is called? Using that electron? Go on, Isabel. I reminded it the other day. It involves the word electron. Yeah, it's electron affinity, right? So good. So it's the electron affinity. So it's that process there. And you might remember that electron affinity, the first electron affinity is exothermic. So you're taking the chlorine atom, which has got one space in the outer shell, and the electron going into that can kind of snuggle up nice and reasonably close to that positive nucleus and goes, ooh, that's nice. And so that's an exothermic process, quite a small exothermic process, but it is an exothermic process. So we're going to call that, label that delta H, first electron affinity for chlorine, right? So we can use this Born-Haber cycle. I'm just going to make this a little bit taller. Still like that, we don't need the stuff at the bottom for now. We can measure this. I'm going to call this A. We can measure B. Look it up in our data books. We can measure C. We can measure D. And we can measure E, right? So if we know all of these other processes, we can work out lattice enthalpy. Now Hess's law, remember, is just clockwise equals anti-clockwise, right? Or enthalpy change is independent of the path taken. So we want to work out the energy change going from here to here, so that we can study this complex idea of lattice enthalpy. So one way of thinking about it is I've got to get from here to here. I can either go this way, but I could do minus E, minus D, minus C, minus B, because they're in the opposite direction to the arrows that are drawn there, plus A. That's the quick and easy way of doing it if you're lazy like me. But there's a much more secure way of doing it that I would encourage and often gets the mark, which is write all the clockwise arrows. So let's go through them. Is B clockwise or anti-clockwise? 3, 2, 1. Clockwise. So we can say, I'm just going to write at the bottom, B. What other clockwise ones are there? There's B, C, D, E, and we'll call this one F. They're all clockwise, right? And then A is anti-clockwise. This one down here. So you can rearrange it to give exactly the same as what I just said. And I've run out of room, so I'm going to write it annoyingly. Sorry, I've run out of room there. Where should I write it? I'll just write it over here. We rearrange that to make F the subject of the equation. It's A, take away all of these things, isn't it? So F is equal to A, take away B, take away C, take away D, take away E. Are we happy with what I've just done there? You can approach it either way round. I think I prefer you to do this, but frankly I know many of you are sort of quick and sharp enough to do it either way round. So I love the fact that once you finish teaching this, it looks horrendously complicated. But hopefully I've gone through it in a way that I'm not going to ask whether you think it was or not, but that's doable, right? All you've got to do, you're often just given the information. They say, can you work out F? Or can you work out B? And they'll give you all the other information. You've just got to plug the numbers in. That's all you've got to do. But you've got to know the definitions too. So I think what I'll do is I'll shut up for a bit, which you'll be pleased to hear. And I'll put as much of this as I can on the screen and let you copy it up. If you finish quicker than other people, then you can start looking at the definitions that I've given you, okay? All right, so that's your basic Born-Haber cycle. I'm going to draw another Born-Haber cycle now, making a different compound. And there's going to be some differences which you've got to look out for. Okay, so I'm going to go a tiny bit quicker. We'll do the same process, but I'm going to go a little bit faster with it, but make a different compound. The compound I'm interested in this time is sodium oxide. So I'm going to draw sodium oxide down there, and you all know the formula of sodium oxide is Na2O. And so already, hopefully we've spotted the difference here, is that sodium oxide has got 2 sodium ions in it. So all the sodium stuff's going to have to be doubled up, isn't it? What I'll do is I'll talk you through it, then you can copy up after, otherwise it's just going to be really tough. I'll give you plenty of time. So producing sodium oxide this time, and we're going to produce sodium oxide from 2 moles of sodium solid and still half a mole of oxygen, but there's another complication here, which is that oxygen is in group 6, so oxide ions are 2 minus, and so we've got to consider that too. What should I do here? Should be magnesium. No, I'll do it this way. I'll point out something else as well. So we've got to go through the same process. So this is delta HF. Forgive me, I'm just going to shorten what I write a little bit this time. Delta HF of sodium oxide. That's still times 1 because it's the formation of 1 mole of that stuff. Got to make now 2 moles of sodium gas. And remember what the enthalpy change I've just labelled is called? Lewis, remember what that's called? This is 2 times the atomization energy of sodium. It's forming 2 moles of gaseous atoms. What's the next process called we do with sodium? Shout it out if you think you know. First ionization energy, right? So first ionization energy of sodium, but we've got to times that by 2 as well. And you can see where these things get a little more complicated. So you've got to double those numbers up when you're going round. Now I'll mention it now, but I don't know why I've started writing over there anyway. I'll mention it now that you might get a Born-Haber cycle with magnesium ions or aluminium ions or calcium ions. You then have to do the first ionization energy and then the second ionization energy to add that extra little bit. Do you see? And half mole of oxygen. So sodium's done, gaseous, but I've now got to do oxygen. I've got to do the atomization energy of oxygen. So far it's similar, except I've got doubling up the number of sodium ions. Right, gives you that. Right, now it gets a bit trickier. And by the way, this I think this one very similar is in your packs, so you can refer back to that. But then you've got to do them separately, and I'll explain why in a second. But that process there, what's that process called, please? Shout it out, Tom. Electron affinity is the first electron affinity for oxygen. That would get you 2 moles of sodium ions, gas, 1 mole of electrons, and 1 mole of oxygen 1 minus gaseous ions, right? And that process is endothermic. But we're not there yet, are we? So we've got to make oxygen or oxide 2 minus ions. Now this is I think the most complicated idea of it, is that process is endothermic. And it's a very common IB question, which is why is the process of first electron affinity endothermic? I'll say that again. Why is the process of the first electron affinity exothermic, whereas the second electron affinity for oxygen is endothermic? Discuss. Have a little discussion there. I'll pause the video, give you something to think. And the answer is Magda. Not sure. All right, don't worry. Lucas. It's already got, what sort of charge has it already got? All right, it's got a negative charge. And what's the charge of an electron? -1. So it's the idea. I think it's in your year 12 mock. I'm sure it was. Anyone remember? So it's 2 negatively charged things. That's the first thing you've got to say. And those are repelling each other. So you've got to overcome that repulsion. you've got to push it together. So that requires energy. Right, so this leads me to the last kind of general point I'd like to make before you copy this up. So both of these cycles we've got here, they basically form the same sort of structure, don't they? The same sort of idea you've got. And in fact, in the packs that you've got, it's set out really nicely as a simplified Born-Haber cycle, I think. So it's this here, like that, right? That's all that's going on really, isn't it? Look, you've got another example down here for you to look at too. But you've got elements in normal states going into the solid ionic compound, gaseous atoms, gaseous ions. You can do these in different orders. It doesn't matter what order you write them in. It's just the way that I like to do it. So you can do atomization energy of one, atomization energy of the other. Or it doesn't matter. You can do it the other way around. So the thing I want to point out here is a kind of general point that you've been lied to, as always, by your GCSE chemistry teacher, which in many cases, well, some of you that was me, and I probably lied to you, or at least omitted some truth. You were probably told at GCSE. I'm going to go back to the GCSE argument here. I'm going to just, this is not really necessary for IB, but I want to remind you of where you've come from, right? You were taught, weren't you, that if you were to take lithium and fluorine, which doesn't exist, by the way, because it's all F2, you were told that electron jumps from lithium to fluorine, right? Making a lithium ion. Does this all sound familiar? Yeah? And, oops. I'm not going to draw the electrons because I can't bother. Oh, well, go on then, I will. There you go, and a fluoride ion. You were told that that happens, right? And you're told that energy is required to remove the electron from the sodium, but the energy is released when you give it to the fluoride, or to the fluorine to make fluoride, right? That's kind of what teachers often teach at GCSE, and that's why ionic compounds form. Why does sodium react with chlorine so violently? Why does magnesium react so violently with oxygen in the air? And you're often told that energy is required to remove the electron, energy released when the electrons are given to the atom, right, to make ions. That's what you've been told, possibly. But it ain't true. If you look at the Born-Haber cycle, that gets you almost nowhere. The ionization, the electron affinity gets you almost nowhere. The reason that ionic compounds form, go back to my first Born-Haber cycle, the reason that ionic compounds form, the reason that ionic compounds are much more stable than the elements they're made from, is this enormous exothermic process in the thousands of kilojoules per mole. So although they don't go through this process in a stepwise fashion in reality, the whole reason that ionic compounds form at all is the enormous energy released, or the strength, is the strength of the lattice. That's why ionic compounds form as they do. Does that kind of make sense? It's this that drives ionic compound formation, this process here. Now, if I were to go another level, which I might do in a future lesson, an interesting thing to think about is why does sodium chloride form NaCl and not Na2Cl, for example? And I've got a little nice little, or ACl is got AlCl, AlCl2, AlCl3. We all know that AlCl3 forms, but the question is why. And you kind of on the face of it, well, they all would have a negative lattice enthalpy. In fact, I think all three have got an overall exothermic profile if you draw a Born-Haber cycle, but it's the size of these compared to the size of everything else which is the most exothermic process overall. But I'm kind of going off on one now a little bit. What I've told you is what you need to know. What I'm going to do is going to put up the Born-Haber cycle for the more complicated one here. Remind you that you've got another one in your pack that I've given you. Get that copied up, and we'll spend I'm going to stop the video in a second, but the last bit of the lesson for those listening or watching will be learning the definitions that you've not yet learnt.